Can you hear me? Yeah. So a bit about me first. I've been a developer on the engine team at Ableton for about 8 years now. And I'm not part of Apple. I don't represent Apple. So some of the things I'm going to talk about are going to be sort of deep and might give that impression, but everything came from my observations and reading of some open source Apple code. So the agenda for today, we're going to first talk about understanding the system. So trying to understand how Apple's modern mobile processors work. Then I'm going to talk about single-threaded performance. And then we're going to switch into multi-threaded performance. And finally look at what can come in the future, so what fixes we might expect. So about understanding the system first. A lot of my talk is going to be about dynamic voltage and frequency scaling. This is sometimes just called CPU throttling, sometimes just frequency scaling. And what this is an approach to save power by trading off performance. So the system will ramp up the CPU frequencies over time in response to a workload arriving. So for example, if your phone is sitting idle, then all of the cores might be sitting at a low frequency, so at 500 megahertz. If you then load a website, the scheduler is going to notice that the increase in load and will then respond to it by ramping up the frequency over time. When the website is finished rendering and the system is idle again, it's going to decrease the frequency over time, and then you're going to get the same energy savings that you had at the beginning. Important to note here is that it's stepped. It's not continuous. So there's a discrete number of frequencies that are possible, and the scheduler is responsible for deciding what the frequency needs to be based on the load. So let's talk about how the processors in the iPhone have evolved over time. So in 2015, Apple released the iPhone 6S with the A9, and that was a dual-core phone, dual-core processor. And a year later, in fall 2016, they released the iPhone 7, which had the A10 chip in it. And here's where a sort of paradigm shift began to occur. So instead of just being dual core, this thing actually had 4 cores in 2 clusters. So there's an efficiency cluster and a performance cluster. And only one or the other can be active at a time. So you couldn't have 4 threads on 4 cores simultaneously. You could only have threads on one of the 2 clusters at a time. Interestingly, I realized, like making this diagram, that the processor numbers, like A10, are perfectly synchronized with the iOS versions. Every year there is a new A series processor and a new version of iOS. So it's sort of incredible how fast the pace is for the hardware development. So then a year later, they released the A11. This changed things again. Now both clusters could be active, and they increased the number of total cores. So now there's 4 efficiency cores and 2 performance cores. And all 6 cores could be active simultaneously. And as usual, the clock speed got bumped a bit. Then the following 2 years were, as far as these specifications are concerned, just clock speed bumps. I think they added a lot of other technology in other areas, but for our purposes here, the number of cores stayed the same, the 2 clusters stayed the same, it was just clock speed that increased. So the paradigm shift that I talked about is the difference between symmetric multiprocessing, which you may have heard about, and asymmetric multiprocessing. So in SMP, all of the cores are exactly the same. So the scheduler can rely on the performance of any given core that it might put a task on being identical to another one. It doesn't have to think about the performance of particular cores. So with A and P, that changed. Now it's heterogeneous, and the scheduler has to manage a lot more. So let's walk through an example of what the scheduler has to do. So let's start in an idle state where there's a few background processes, that's these tool icons here, that are running on the system, maybe checking for things like notifications. So the scheduler might decide to put all of the efficiency cores at 500 megahertz. So then, let's say that I start loading my website. It will start on one of the efficiency cores, and also the frequency will ramp up of the efficiency cluster. Also, important to note here is that all of the cores in a given cluster have the same frequency. They're not, as far as I've been able to observe, individually addressable. So it'll then migrate that thread, the Safari rendering thread, onto a performance core, because it's noticing that the workload has continued, and it'll also bump up the performance of that cluster. Then it'll lower the frequency of the efficiency core to save energy, because it's no longer doing anything expensive. And it'll, again, ramp up the performance cluster frequency so that it can get maximum bandwidth rendering the website. So that's that. As you see, this is a sort of delicate balance between energy usage and performance. And pro audio is a niche where latency and performance are super critical. And an important thing to think about as well is that it's not necessarily desirable to process as fast as possible. You might not want your buffers to finish as quickly as you can. You actually want to save energy when possible. And sometimes that means running at a lower clock speed and buffers taking longer to compute so that you can do it. What's important is that you don't have dropouts. You need to meet the deadline, but not necessarily always run as fast as possible. So while researching this talk, I ran across this patent. This is the best documentation I've found about all of this. I've never read a patent in full before. It's sort of crazy legalese mixed with understandable engineering language. There's a lot of really complicated diagrams in it. And I give my simplified version of it all now. So there is this thing called the Closed Loop Performance Controller, CLPC. It is a closed source part of the XNU kernel and closely integrated with a scheduler. It takes a number of factors into consideration as inputs. So it considers audio deadlines, the I/O rate, how fast you're reading from the network or from disk, thread utilization, which is probably what most of you think would be the main input here. So over a given time window, how much time did a thread spend on a core? Power usage, the instruction rate, which is subtly different than utilization. The temperature, apparently not just the die temperature, but the temperature of the enclosure is modeled somehow so that customers don't complain about their hand getting hot. And also the energy that's available from the battery at any given time. And the results of all of these inputs, and so the results of this process are thread scheduling decisions, which means which thread gets put onto which core, how long does it last there, which cluster does it go on, and also DVFS states, so which, for the two clusters, what frequency are they running at? So there is one particularly interesting part of this diagram for us, and that's in the upper left-hand corner here. So there's this thing in user land called, so audio is mentioned here, that plugs into work interval utilization, which then goes into a bunch of other stuff. So what is this work interval utilization? If you Google around, you will stumble across some private code in the XNU kernel. And it's an interesting API to understand. So this is used internally in iOS in Media Server D, and is used so that the system can declare to the scheduler and to the performance controller how long a real-time task is taking. So it declares the start time of a work unit, so a buffer, what time it actually finished, what the deadline is, and what the next start time is. And the information is actually reported after doing the work, not before. Yeah. So this is actually used to feed the CLPC. And yeah, so that's enough about understanding the system. Now I'm going to talk about single-threaded performance. So, and to do that, I'm going to be using an app that we wrote called Audio Perf Lab. And the idea here was to write a real-world app that produces audio to demonstrate the problems. Because we're also focusing on multi-threading later, and I didn't want this to be purely a theoretical exercise. So the idea is that you have a lot of parameters, and you can try different workarounds, and also see where there are dropouts audibly. So I'm going to show a demo with that. Okay, so what you hear right now is additive synthesis. So it's playing a unison saw chord, and you can set the number of sine waves so that you can basically simulate an increase in workload. Here's what that sounds like. Oh, there was a dropout. I was supposed to do something. Okay. Yeah. So you can set the buffer size. You can set the number of sine waves. The sine waves are computed in a sort of naive way intentionally using stood sine. So you could do this much faster and get many more sine waves if you did it properly. But for us, that's fine because we just want to create some workload. It's multi-threaded, so it will distribute the sine waves to different threads in chunks. And there's a few visualizations as well. So up at the top here, there's, oh, I can't use this right now, I don't think. No. So up at the top, there's load, which is showing the percentage of a buffer duration that was spent processing. So as I increase the number of sine waves, you see that the load goes up. There's work distribution, which only makes sense when there's more than one thread. This is showing how the sines are distributed between the two threads. So if only one thread was working on all of the sines, then it would be all black. But here, actually, it's distributed evenly, which is what you want. So you see half blue, half black. There is cores. So this is actually showing where the audio threads are being scheduled onto which core. The first 4 rows are the efficiency cores. The last 2 are the performance cores. So right now, with a low load, you see that black, which is the core audio I/O thread, is sort of switching between various efficiency cores, and the worker thread, which is blue, is mostly running on one of the performance cores. And if I increase the load, it'll switch so that all of the sines are being processed on the performance cores. It stays there for a while. So the behavior is sometimes hard to understand. So those, oh, and then there is energy. So there's actually a mock API that isn't well known where you can ask for the number of nanojoules consumed by a given thread. And that is what I'm using here to make this graph, and also to show watts over time, or to show the watts text. Okay, so then I wanted to actually show the issue that occurs with single-threaded processing. So if I drop the number of process threads to 1, and to exaggerate the effect, I'm going to increase the buffer size so that we get a really big dropout. Then I press burst. I didn't describe burst. So when I press the play button, this is going to increase the number of sine waves all at once to whatever the number is. It's going to hold it there for half a second and then drop back down. And the idea there is to be able to experiment with what happens with a dramatic load increase all at one time. So I'll turn it up. Okay, so big dropout. So interestingly, if I just gradually increase the number of sine waves, the system has no problem handling the load. The issue is with the sudden increase. Okay. So this tool is available on Ableton's GitHub. If my colleague pushed the button. Yeah, so you can check it out, and actually, I'm going to be showing some workarounds later. You can actually see how the workarounds are implemented concretely. So a real-world use case where this comes up is playing a lot of voices on a synthesizer simultaneously. It doesn't necessarily need to be 10 people putting their hands on the keys at the same time. It can be unison, where you have lots of detuned voices, where you play a 3-note chord and suddenly you get 15 voices created. So you have some real-time input, and the load in the real-time thread increases all at one time. So now I'm going to show some measurements. The idea is it would be nice to understand how the hardware reacts to changes in workload with graphs and with numbers instead of just interactively. And the most direct way to measure that is actually by seeing what the CPU frequency is over time. In Audio Perf Tool, I don't have that right now. It's just showing the load. So the idea is to actually graph frequency over time in response to a load increase. So we need some tools in order to be able to do this. The first tool is the ability to measure CPU frequency. So there was an API for doing this. At some point, it got turned off. It now always returns an error, which is sad. So we have to find another way. Here is the other way. When reading this code, you have to pretend that the optimizer doesn't exist, because in reality, it's going to be inline assembly. And the idea is to run a bunch of subtraction operations and to time the amount that takes. And they're a dependent chain of subtraction operations. So we want there to be one cycle per instruction. And we can ensure that by working on the same variable. So not decrementing several variables, but just the same one over and over again. If there was many variables in play, then they could potentially be parallelized by the processor automatically, and then you would get more than one instruction per cycle. So so basically we have this unrolled loop where there's 32 subtracks per loop iteration, and we have 512 loop iterations. The reason for that is because the branch might take more than one cycle, so we need to amortize the cost of that. So we know the number of cycles. That's 512 times 32 here. We know the duration because we're going to time this whole block. So then if we take the number of cycles divided by the duration, we get the frequency in hertz. So I didn't invent this. There's actually a nice blog post by Danjeli Schembri that describes different trade-offs and shows the assembler for ARM. So the next tool that would be nice is the ability to know what the current CPU of execution is. And there's actually a way of doing this as well on ARM by reading a particular register that the kernel sets. And this will return the current CPU that the thread is executing on. So with these tools in hand, I'm going to show how the tests actually work. So first, there is a phase where we're going to measure the idle frequency. Then at time 0, the test will actually start. And during the test, we're going to measure, so meaning that the workload suddenly increases at that point to near peak performance. And then during the test, we're going to measure how the frequency ramps up. So these are the graphs that result from the test. And to explain, you have in these rows a buffer size. So here's 256, 512, and 1K. And on the x-axis, we have time. It's not so much time, about 100 milliseconds. And on the y-axis is processor frequency. And there are the 6 cores marked with colors. So you can see where a core migration takes place. So, and here are buffers. So the start of one of these rectangles is a real I/O callback, and the end is the deadline. So if you are exceeding the end of one of these rectangles, then there's probably a dropout. And in the first, in all of these buffer sizes, there is actually a dropout. So there's a massive gap here. And actually, the first buffer is taking almost twice the amount of time that it should. This is on iOS 12. Yeah, and you can see a few interesting things here. One is that the frequency increases are discrete, as we're expecting. Also interesting is that the core migration is taking place mid-buffer. So you don't necessarily stay on a given core for an entire I/O callback. You might be migrated. And after it migrates, once it's on the performance cluster, which is the red and yellow colors, it's running at the maximum frequency, actually, and stays there. So those are the numbers, or those are the measurements for iOS 12. In iOS 13, things changed a lot. Apple improved things. They actually added a new scheduler called AMP to the kernel. And here's how it looks there. If I switch back and forth, you can see how much better it is. We're still dropping out, but the transition to the performance cluster takes place much quicker. So to look at the number for 1K buffer size, it takes about 13 milliseconds before it transitions to the performance cluster. I think that's all I wanted to say. So to prove that this is an issue on the latest processors as well, and not just the iPhone X or 10, here's the measurements on an A13. There's also dropouts, but it's still better. You also can notice that the maximum clock frequency is higher, as expected. So it jumps up a bit. But for this workload, we are still dropping out. So now, what are some possible workarounds for all of this? The first idea is, what if we add some sort of artificial work to the I/O callback so that we trick the system into thinking that we're doing DSP the entire time, even though we're not, so that it keeps us ramped up constantly. So to show this graphically, we have DSP work, which might have varying lengths depending on how much work there is. So here it's a bit longer than the second time. And we're going to add a block of artificial work such that the duration of work in any given I/O callback is constant, and also so that the driver gets a constant margin to shuffle around buffers. So we're going to spin in this artificial work, waiting for some target time to maintain this total constant time. The question is then, what sort of artificial work can we do? It turns out that not all artificial work is the same. So some instructions are more energy efficient than others. The best that I've found is this thing called the WFE instruction, which is ARM specific. It's wait for event. It's used in the kernel to implement a delay function. And it causes the processor to enter into a low energy state and stays there for about a microsecond. So, and I found that this is actually much better than just a yield instruction on ARM or a no-op instruction or any other type of thing that I've tried. And you can read more about it in the ARM architecture reference manual describes exactly how the mechanism works. So what happens when we try this? So what you see is that before the test begins, we're already running at not maximum, but near maximum frequency, and that the dropouts are gone. So when the test starts at time 0, we are already ramped up and already running on the performance cluster, which is awesome. So what are some pros and cons of this? The pro is that it'll probably work forever. A con is because the system doesn't know that you are not performing DSP, basically. A con is that it's not preemptible. So if you have other threads doing things like drawing the UI, drawing animations, they cannot take time away from the audio thread. You're stealing time that can't be preempted for other threads. You're basically making the entire system slower by virtue of blocking here. Another thing is that it blocks background apps. So the way Core Audio does background audio rendering is it goes from one process to another in a loop, all on one thread. So it says, one app, give me your audio, then goes to the next app and says, give me your audio. The thing is, if one of those apps is trying to occupy 90% of the buffer duration at all times, you're not giving any time to other background apps. So this is a pretty big disadvantage if you want to support background audio. Another thing is that it has higher energy usage than if you weren't using artificial work at all. And I have some measurements. I think I'm running slow on time, so I'm not going to mention these, but you can see later. So I think, Phil, I see in the audience. So Google has been talking about a lot of this for various ADCs at various conferences. The left is Google I/O, and the Google Oboe library actually implements artificial work in the stabilized callback class. This is not my idea. So let's move on to another workaround idea. So what if we were to create a background thread that just does busy work? So I noticed while in Audio Perflab sometimes that when animations are running, so when the visualizers are drawing a lot, then somehow performance was a lot better. So the idea was, okay, let's make it not dependent on what views are showing at a given time, but rather create a thread that's always doing work. So the idea is to have this busy thread, and the same artificial work, the WPE instruction, is going to run in a busy thread. In order for iOS not to terminate us when we're running in the background, we have to sleep also. The third of the time we're going to sleep. So how does this look? Well, it's not as perfect looking as before, but it's still pretty good. So when we start the buffer, we get put onto an efficiency, onto the efficiency cluster. We're not running at maximum frequency, but for this workload, we don't drop out. And the reason this happens is because all of the cores in the cluster run at the same frequency. So just because the busy thread is there doing work, it has to ramp up the entire cluster. We will get put onto another core. We won't get put onto the same core as the busy thread, but all of the cores have the same frequency, so we benefit from that. What are the pros and cons of this? So artificial work can now be preempted because that busy thread will set the lowest priority possible on the system so that everything else will preempt it if there's some work to do. Background audio isn't blocked, and the energy usage is a bit better. There's the numbers. A con is that, as you saw, we're not running on the performance core from the very beginning. So performance could potentially be a bit better. So let's try yet another thing to see if we can get rid of that. So this idea is that we're gonna keep the busy thread, but we're going to offload DSP work to a worker thread. So instead of actually doing DSP on the audio I/O thread, we're going to ping pong between another thread, which is going to do the real work, and we're going to use synchronization primitives to wake up the other thread. So graphically, at the beginning of an I/O callback, we're going to wake up a worker thread. Then there's going to be a block of DSP work. While that work is happening, the audio I/O thread is going to block in a semaphore, waiting for it to complete. Then the worker thread is going to notify it, I've finished my work, and we'll then return to the OS. And then the worker thread is going to wait on its own semaphore for the next activation. So if you don't know what a semaphore is, just know that it's a synchronization mechanism that where you can post and wait, and that allows you to do this sort of synchronization. And the same process repeats for every subsequent buffer. So the worker thread is going to be a high priority, what's called a time constraint mock thread. And the difference between the worker thread here and the I/O thread is that the worker isn't part of that work interval that I showed at the very beginning. So core audio threads are actually special because they're part of this work interval automatically. That's not something that you can normally achieve by creating a thread on your own. So basically by opting out of this work interval mechanism, we're being treated differently by the power management system. So how does it look now? So it actually gave us similar performance to just doing the artificial work in the real-time thread, but without doing it. So we're not running at the maximum clock speed, but nearby, and when we start the workload, we're already ramped up. So this is currently what I see as the best workaround. It's more complicated than the others, but it seems to have the best trade-offs. The question is, why does this work? And I've done some experiments and noticed that by using the private work interval API and actually leaving the work interval from the I/O thread, which is verboten on the App Store, so it's just an experiment, we can get similar results. So that means it is the work interval that's causing this. It's still not entirely clear why having the busy thread affects the higher priority worker thread so much. So it could change in a future scheduler. So the pros and cons here is that we're getting solid performance. As before, the work can be preempted, background audio isn't blocked, and there's also good audio, good energy usage. It's the same as the numbers that I showed for the busy thread before. And the cons is, like I said, this is depending on the current iOS scheduler behavior. We need to constantly check for new iOS betas that this trick is still working. So now let's talk about multi-threaded performance. I think when you talk about, first I want to say, so it would be great to be able to double the amount of audio processing on the last 3 generations of iPhones. That is the motivation here. Like, not just use one of those performance cores, but use both. It would be pretty awesome to be able to do that. And I think most people fall into one of 2 camps when thinking about multi-threaded audio. So either render everything ahead of time, so maybe have some medium priority worker threads that are rendering audio a few seconds in the future, or do everything immediately. So for a given buffer, you're going to render all of the audio necessary for that time slice. The former approach, ahead of time rendering, is nice when your application allows it because it'll smooth over dropouts. You can have a lot longer buffer. Some applications, though, need everything to be as responsive as possible because of certain features, so they can't do that. They need to have immediate rendering. So in live, an example of where immediate rendering is necessary is scene launching. I'm going to play this short example. When the second scene fires here, that's the scene that has a bunch of clips in it, there's a dramatic increase in workload. So the application doesn't know what scene you're going to fire at what time, so it doesn't have anything to render ahead of time. It needs to be able to respond to any user input as soon as possible. So how will multi-threaded processing work? It's pretty similar to the workaround that I showed before, the deferred DSP workaround. The idea is that at the beginning of an I/O callback, we signal a DSP worker thread that work has begun. It's then going to perform DSP work. So both the worker thread and the audio I/O thread are going to perform DSP. Then the I/O thread in this case is going to wait on the worker thread because the worker thread took longer. Then the worker thread is going to signal back to the I/O thread that it finished, and then it's going to return to the OS. And this process then repeats for every subsequent buffer. So all of the details of how to actually distribute the work, I'm not going to get into right now. This is just the basic high-level thread synchronization mechanism. And this is the model also that, that Audio Perf Lab implements. So let's look at how the performance is in Audio Perf Lab when we implement this. So if I set the buffer size to 64, which is super low latency, it's to, again, exaggerate the problem. So if I then pressed burst, so massive dropout. So a lot worse than before, actually, and for the single-threaded case. And when I increase the sine wave slowly, also not working at all. This is on iOS 13, by the way. So I can unfreeze the visualizations to see how the cores are looking here. So what you see is that, well, the behavior changed when I unfroze the visualizations, about in the middle here, and because of the increase in workload that the visualizations cause. That's why there's this freeze button, because it can cause sort of this confounding effect where just by virtue of having the visualizations on, the performance is changing that you're measuring. So before I had them on, you see that the worker thread is running on the efficiency cluster, and that's the problem. It's running on a much slower cluster. And then after I turned them on, it switched. So this is a strong hint that the busy thread approach is going to work here as well. And I'll show that now. So if I increase the busy threads to 1, and I freeze the visualizations again, then everything is smooth, and I can also increase the workload without a problem. Also, this is 64 sample buffer sizes, pretty low latency, and everything is working fine as long as I have this background thread doing work. Okay. So if we look at this graphically, this is the behavior without having a busy thread running. And you see that you see 2 threads here. This is the core audio I/O thread, and this is the worker thread. And you see that the curves are entirely different there. So for the core audio thread, we get put onto the performance cluster right at the beginning at a high frequency, and we stay there. But for the other thread, we actually get put onto the efficiency cluster, and the frequency varies in a sort of confusing way, and we're getting dropouts the entire time. This is this big dropout that you heard. And eventually, though, it switches to the performance core, at which point there's no more dropouts. Yeah, ideally what we would see here is that both threads are running on one or the other core of the performance cluster. So we want to see red on one side and yellow on the other side, ideally. So how does this look if we use the same workaround that I showed before? Not just the busy thread, but also delegated DSP with this proxied DSP. So it's looking like what we want. We have buffers running on the same core for an extended period of time, which is also good for the caches. And we don't have the efficiency cluster being activated at all. And of course, there's no dropouts here. So another question you might have about multi-threaded audio is how many threads should I create? Given that there's 6 cores, why can't I create 6 threads? So let's try to create 6 threads, 6 audio workers, and see what happens. So it looks very colorful, and what's actually happening here is context switching. So all of the threads are placed onto the 2 performance cores, and the scheduler is rapidly switching between them. So you just experience the sort of context switching and synchronization overhead with no benefit. So this is purely scheduler dependent as far as I know. It maybe could schedule threads onto all cores, but it chooses not to. So the answer to the question is 1 DSP thread per performance core. And there's actually a private pthread API that confirms this. It returns 2 on iPhones, which have 2 cores in the performance cluster. So what is the future outlook for all of this? So there's originally, I wrote Audio Perf Lab to include in bug reports to Apple, actually, a year ago. And I decided, because I put so much work into it, to make a talk out of it. So those bug reports are here. So you can lobby to your local Apple representative. This was filed a year ago, roughly, and so there's 2 bugs. One focuses on single-threaded performance, and one focuses on multi-threaded performance. And those are the two parts of the talk. I think that the single-threaded performance is, it would be nice if it was better, but it's understandable behavior from the system because of frequency scaling. The multi-threaded bug seems, or issue seems like a real bug, because you should be able to do this. And it's not just a matter of tweaking or sort of getting more performance out of the system. I would say that for the single-threaded case, the behavior is fine for a lot of workloads. It is an issue if you're near the maximum. So if you're trying to do a lot of DSP, which isn't the case in most apps. For pro audio apps, it is. And the multi-threaded issue, I think, is something that can be fixed. So one possible direction for a fix for the single-threaded case is described in a research paper for Android. It's called Energy Efficient Low Latency Audio on Android, and it describes, they did a lot of measurements and experiments for exactly this problem. And there's an interesting quote in it: "The reactive nature of CPU frequency driving from kernel space cannot be easily fixed without explicit hints from user space." And they propose an API so that the application can notify the OS before a workload change comes in. Yeah? So that the system can respond in advance before the actual processing begins, instead of having to react to it. In the CLPC patent that I showed earlier, there's also a long quote. It's really nice. I'm not going to read it now, just to have time for questions. But they also propose this API, basically. So Apple has thought about this. It seems maybe that it's ongoing work or something. There's a certain amount of trust that has to be given to applications that they're declaring the right workload before it occurs, so that an application doesn't simply say, OK, I'm going to do a lot of complex processing, and then the user's battery gets drained. But it could be a direction to fix this. So the idea would be that when I press all of those notes on the keyboard, I declare to the OS that the workload is going to increase. And then the work comes in on the real-time thread. So what are the takeaways today? So the modern mobile processors have a lot of new challenges for low latency audio. It's not just frequency scaling from x86 days, but also this new AMP paradigm. Through measuring, we've been able to gain a lot of insight into these challenges. And this one approach, this one workaround, busy thread plus deferred DSP, is the best workaround that I know at the moment. And I hope that by discussing these issues openly, we can demonstrate the importance of these things to vendors like Google and Apple, and hopefully in the next years improve performance here by default. Okay, thanks.
Do we have any questions?
What is the battery performance of this?
Say it again?
What is the battery performance?
Of the workaround that I showed?
Yes.
Yeah, so do you want to know like how long the battery life is? So I had the energy usage metrics that I showed there. It's reasonable. It's a lot less worse than I would have expected. because it's using this WPE instruction. All I've done is use this particular API to get the energy usage at a given time. I'm trusting that it's accurate. To really do it thoroughly, you would need to run tests where you you launch the app using the workaround and then measure how long it takes for the battery to drain. Yeah. Or I know there's also devices that Google uses to measure energy usage, like at the hardware level, which would be even more accurate as well.
So when is Live being launched on iOS? I'm joking. So you mentioned you use the ARM64 instruction, wait for event. Can you just describe how effective that is against, you mentioned you tried yield. Like, did you do any like in-depth comparison?
I did. I can talk to you after. I think it was like, I did actually measure it. I think it was like 8 times better or something. It was pretty significant. Yeah.
Awesome, thanks.
So when you're using the busy thread, it seems like your DSP worker thread just happens to get the performance core in the single threaded case, but we don't really know why it just happens to get it, and then
it's also scheduler behavior right now. That's right. Yeah. Exactly. I mean, it doesn't get it from the very beginning. It is put onto the efficiency cluster at the very beginning, just with the busy thread. But it's running at a higher frequency, so I think it switches quicker. Yeah, and it gets a higher frequency, which is beneficial at the beginning.
One last question.
Hey, did you try out the research paper suggestion of saying, like, I know there's going to be like 36 voices coming up, and then preempt that with artificial work before actually doing the audio work?
I think you couldn't create artificial work quick enough. So the scheduler has to be able to observe it, which is going to take some amount of time, so milliseconds. Yeah. So I think you would have to really have a dedicated API to be able, so that the system isn't being reactive but proactive, basically. Yeah.